Hey SMARS fans, how you doing? I hope you're having a good Sunday. So this is quite a fantastic show we've got lined up for you today. We're going to be looking at artificial intelligence, machine learning, SMARS, object detection. Oh, it's all awesome for today. So I can see a few people joining now. Hey Samo, hope you're having a good Sunday evening or whatever time it is where you are. So without further ado, let's have a look at what this show is all about. So let me just bring up my notes. So do you want to build your own robots? Don't know where to start, what you'll need, or how to do it? Then you're in the right place. And if you stick around, I'll share with you a free giveaway too. So my name is Kevin. Come with me as we learn to build robots, bring them to life with code, and have a whole load of fun along the way. So this week we'll be looking at OpenCV, which is computer vision, open source computer vision, and it's a software library. We're going to be using that with Python. I think it actually works with most languages, but we're going to be using Python because that's the language of choice for the Raspberry Pi, and we're going to be using that to enable our SMARS to detect faces. So it's so cool. I'm going to be showing you this live today. We're going to also be looking at machine learning, how it actually works, because it's one of those things that's talked about quite a lot at the moment, and it's kind of a bit what am I trying to say here? People will assume that this is some kind of black box that's unknowable, or it's some very sophisticated technology that works like magic, or is just really high tech. It's actually really basic, and we're going to look at how it works. It's basic in the same way that a computer is basic, that it just adds numbers together. We're going to be looking at how machine learning works and getting into the sort of nitty gritty of that. Stick with me. It's simpler than you think, but also a bit of a rabbit hole. So fascinating stuff. So we're looking at why machine learning needs special hardware, like the new Apple M1, which I'm currently using. So that has a dedicated 16-core area for doing machine learning. It's the training part that requires this extensive piece of technology, piece of your CPU to do this. So let's get on to the slide deck. So let me bring up, you might have noticed as well, we're back in Ecamm Live, which is my favourite suite for showing things. And we've got some nice new design of slides as well. So let's get on to this now. So the goals for this series have been, we want to build a SMARS Quad. We did that on episode 1. We wanted to make our SMARS walk and be controlled by a web interface. We did that last week, and this week we're going to be making our SMARS see and process video to detect faces and objects using something called OpenCV. Next week we'll be making our SMARS talk and respond to voice commands, so that will also be pretty cool. So what is OpenCV? OpenCV is open source computer vision library, and on their website, that's their little logo there as well, it says an open source computer vision and machine learning software library. It was built to provide a common infrastructure for computer vision applications and to accelerate the use of machine perception in commercial products. Being a BSD licensed product, OpenCV makes it easy for businesses to utilize and modify the code. So if you think, what's a BSD license? That's a Berkeley Standard Distribution. It's a bit of an in-depth thing to go into here, but essentially, way back when there was only a few big companies that made computers, like mainframe computers. A lot of them ran Unix. And there were several flavors of Unix around. And initially, it wasn't really considered by the manufacturers to be something that they would need to, make money on. So they kind of gave away the source code. And then other companies were like, whoa, hang on a minute, that's our intellectual property. Let's not give that away. Somebody else might start making money off that and we don't get a cut of that. So there became a bit of a Unix wars situation going on. And, there was like Sun Microsystems, there was... who else was they back in the day? Berkeley, which is the University of Berkeley. They reverse engineered some of the Unix, and by creating their own version of this software, they were able to say, we're going to make a new kind of license where we give this away and we don't care what you do with it. You can make money off it, you can continue to develop it, you can just leave it as it is. We don't care. Here it is to the world. So BSD licenses they're the kind of ones that you're after. If you look at Linux, that uses a different type of license called GPL. which is like a GNU public license. And that's slightly different in that you have to give the source code with the software that you develop. So if you take this open source software, you can bundle it and do things with it and enhance it, but you have to give that original one to the person next in the chain that you're selling this to. So you can make money, but you've got to give them that. BSD, you don't have to do that. You can just sort of use it. So that's why that's quite a significant thing, and that's why OpenCV is really widely used, because there is no strings attached. So I thought I'd just share that bit of an insight with you why that's an important statement. So let's get right into it. How does machine learning actually work, and how does OpenCV work? So if we look at these steps on the screen, so the first one we've got there is an image of just a face, one of my robots, Sonny. So I take a picture with a camera, and what that camera essentially does is it's digitizing what it can see through the lens. So the little CCD device will pass to the image processor an array of pixels, and the colours of them, if you look at that little sort of call out that I've got, most commonly it's red, green and blue that people use to represent colours in computer vision. So red, green and blue, RGB. Your monitor will have an RGB array of pixels on it. And just by making the strengths of them values, the RGB values, higher or lower, you can make different colours. You can make different mixtures of colours. So you think, how do you make yellow? Well, you might mix some of your, is it green and blue to make a yellow? I can't remember off the top of my head. It's something like that. And the values go from 0 to 255. And if you've been around computing for long enough, you know that that's 1 byte. That's 8 bits of information. So to represent 1 pixel with RGB values, you need 3 bytes. So when we're detecting faces and things, we don't really care about colour. Colour actually doesn't enhance the process. It doesn't give us any extra information. So what we actually do is just throw away all that colour information and just go straight to grayscale. So that's quite a simple process to do. And that step of moving from 3 bytes takes us to a single byte. So we can represent a grey value between 0 and 255 as well. So that's the second step, is that, convert to grayscale. And then you can see on the very right hand side there, we've got this kind of sliced look. So instead of, when we think about a computer image, we think of it as being, a pixel grid. Computers don't think like that. I mean, they don't even think, they just process things. And really, it's just a very long array of values. So if we go to the next one there, you can see that sort of what was a grid of things sort of stretched out into an array of pixels. And then rather than thinking of them as colours for a second, they are just numbers. So it's an array of colour values, essentially. And as you can see there, we've got 104, 138, 131, 101. And if I just jump back a second, I did actually digitize that image there into this image here. And those are the actual colour values of that particular cell. And those are the actual values of each one of them. So you can see there, if we have a very dark image there, we're getting very low values, like, the closer to 0 is black. Closer to white, we've got 186 there. The closer to 255 we get. So everything in between is shades of grey. So 255 shades of grey. Yeah. So how does OpenCV work from a neural network point of view? So what we need to look at there is, what is a neuron? So neural networks are modelled on how the human mind works, how brain cells work, and it's the interconnections between these neurons that makes the thinking happen, that makes the intelligence happen. So we have a neuron. It has inputs on one side and it has outputs on the other side, and in the middle it has weights coming into that. And the weights are essentially just another number that we're going to use to process the inputs to the outputs. And that process is just a simple maths function. And we're going to actually see what that looks like in a minute. And the reason that we change the weights is that we want to be able to make this model learn, but in a way that we're not specifying directly saying that, a face has to look oval. We don't even tell it that. We just show it pictures of faces and it will figure that out. And it will figure that out by looking at adjusting these weights and seeing, does it get more or less like what we're actually asking it to produce. So these neurons are interconnected. At the input layer, that's where our pixels are coming in, our grayscale values, and each neuron has an output that connects to the next layer and to the previous layer. And I don't know if you can see there, but each one of these is interconnected. So every neuron connects to every other neuron in their layer. And the number of layers that we have defines the sort of sophistication and complexity of the model. And the connections are weighted. So each neuron receives weights. And the training algorithm is the thing that adjusts those weights. So we'll look at that in a minute. So those little lines between, they're essentially representing this weighting value from one to another. And you can see there, as we're getting a more complex view of this now, so on the left hand side we've got all our numbers coming in. They're going into the first layer, and that's going into the second layer and the third layer, and then the output layer is the last one in that chain. And what that outputs is a value. It'll be a value between 0 and 1, or you can look at that as a percentage, 0 to 100%. And that means that it's going to give us a confidence that it's found something, and we can actually see where the boundary of what it's found as well. So again, we'll get into this in a minute with some practical demonstrations of this. I just wanted to sort of, as an overview, talk through how this works. And then the other thing that we do is we have training data. So in this case, we might have 1,000 pictures of faces. And we would slice that training data into halves. We would 500 on one side and we would have 500 on the other side. And we will only ever train our neural network on one half of that training data. So it will see these 500 faces, and then the ones that it's never seen, we then use in the training algorithm to see, did it get it correct? So here's an image you've never seen before. We're not going to adjust any weights. We're just going to see if you get it right. And if you get it right, then that means that the weighting that we currently have is more correct than previous iterations of this weighting. So if it gets an image wrong, that information can help go into the training algorithm, which can say, right, something wasn't quite right with this image, whereas this image was good. So it will adjust the weights for each one of those interconnections between the neurons. And the algorithm might say, adjust them randomly at first, and then as it gets things more right or less right, it will adjust them higher or lower. And again, these are just a value between 0 and 1, or 0 and 100%. For each one of these weights. So let's have a look at how these weights actually work. So if we've got on the left hand side our inputs, and again the inputs are just numbers, it's just pixel values to begin with on our first layer. The weights themselves is just a number between 0 and 1, and we simply multiply the weight by the pixel value. And so in this case we've got 104 times 0.5, we're just going to start in the middle. So we get 52, we have 138 times 0.5, and we get 69, we get 131 times 0.5, and we get 65. We add all those together, and we get a number, which is 186. Now really, we need a number that's between 0 and 1 to pass it to the next neuron. So we need to do something that makes this value the correct scale, because it might actually be a really, really small number once those pixel values, if they were all very nearly white because it was a white background, we'd get really small numbers. Whereas if they were all black, we might get massive numbers. So we need to think of a function that we can use that always returns a value between 0 and 1. And that function is called sigmoid function. So it takes a number, or a series, it takes a number and it will apply this formula to it. It uses something called Euler's number, E. And Euler was one of these people, a bit like Pythagoras. He came across a number which was, is it called an irrational number? And he actually figured out what it was. It's 2.718, and then there's lots of other numbers after that, a bit like pi. It's one of those very large numbers that goes on and on. But you can figure this out by repeating particular calculations. Anyway, we use this to figure out, from a number that's passed to us, we can make that into a number that's between 0 and 1. And we can do that consistently using this sigmoid function. You can see there that sort of S shape. So if we have the number from the previous one, which was 186, then if we look on here, 186 would be somewhere around here. So it would be somewhere approaching 1. So it might be 0.93, something like that. And that means we can run that output that we've applied to those weights. We've weighted all our inputs, we've got a number, we've added them together, we've got that 186, we've applied the sigmoid function to it and got 0.93 or whatever it is. That then gets passed to the next layer. So that's this sort of theory behind how neural networks and machine learning works in a really, really quick 20-minute explanation. And the next step really is for us to get OpenCV installed on our Raspberry Pi. So the giveaway I was talking about before, I've created a cheat sheet for you how to do this. It's a PDF you can go and download now. If you go to action.smarsfan.com/OpenCV, you can register and get your copy of that completely for free, no strings attached. I'm going to follow that now, and we're going to install OpenCV as much as we can on the Raspberry Pi Zero. Now, one of the issues with this is these Raspberry Pis are quite underpowered. There's not very much going on in the brain of this. So I have got, I'll look at my overhead, oops, sorry, my overhead. We can see this Raspberry Pi Black over here. And let me just make sure my sound is still working. I think we're all good. Yeah, I can still hear myself. So that Raspberry Pi Black over there is a Raspberry Pi 4, so it's quite a bit more powerful than the Raspberry Pi Zero. So I've installed and experimented on that, and the next step is to install that onto the Raspberry Pi Zero. Like I said, there's quite a few steps to doing this. This isn't just like a very simple package installation. It gets a bit more interesting than that. So let's go and do that now as much as we can. There will be a point where the Raspberry Pi will have to start compiling something, and it will take hours. It could take 9 hours for it to compile this, so it's kind of a leave it overnight and come back to it in the morning kind of job. On the Raspberry Pi 4, it takes about an hour to do, so it's that order of magnitude quicker, and that's got about 4 cores and they run a lot quicker. It's got more RAM as well. So let's have a look at what we need to do next. So if I go over to, let me just make sure I've got this loaded up. So, well, first of all, before I show you that, shall I show you what this actually can do? Because I think that's the kind of payoff, isn't it? That's the interesting bit. So let's have a bit of a screen share on here. So this is my Raspberry Pi Black, and what I've done, I've already installed everything that we're going to install in a minute. I just want to show you the results of this. And so all I need to do is type in Python OpenCV test, which is a very small program that I've written. And what that will do is it'll grab from the camera an image, and it'll tell if it's detected faces, and then it will save that file into an image file. So let me just grab the folder. Let's go into Documents, OpenCV Stuff. And this is the file that it's just created now. Very flattering picture of me just there. So if I turn to the side and I give it a thumbs up, so I'm going to, what I'm going to do is I'm just going to give it a thumbs up like that. So let's go over to there. I'm going to run it again. Let's see, this time it's detected a face this time. So let's have a look and see what we've got. So if I now open up that results, you can see there I'm giving it a thumbs up. Let's try and zoom in on that a bit so you can see what's going on there. So there I am, giving a bit of a thumbs up. So that cyan coloured box that's around my face, that's it detecting that this is the area where it thinks there is a face, and that it's found a single face. If it finds multiple faces, it'll draw a box around each of them, and it's quite confident that it's found a face there. So that's what we're aiming for at this point. Once we have that, we can then do things with it more programmatically. So we could say where in the picture is that, because we want our robot to turn to that, or we might want it to sort of say hello, or whatever we want to do. This is the first step. So that's what we're aiming for at this point. So it looks quite simple as a thing to as an output, but there's quite a lot behind to get to this point. So I basically spent my weekend running this and getting this to work, and then creating the cheat sheet for you so that you could all do this as well. So hey James, how you doing? Welcome to the stream. I'll just pop you on the screen there so you can see yourself. So yeah, hey to yourself. So what I'll do, I'll come back to, if you want to ask any questions or say anything in the chat window, I will come back to that. I've got a sort of section of the show to do that. I've kind of segmented the show just to give a bit of a flow to the show. Right, so let's have a look at, so that was my Raspberry Pi Black. I have another Raspberry Pi, which is this one here. So let me just, it's got a smaller screen because there is it's a Raspberry Pi Zero. I don't know why it defaults to that smaller screen size, but there you go. So what we will do, we'll open up a window and we will start doing what we need to do. So the first thing that we need to do is bring the Raspberry Pi, make sure it's up to date. So we do sudo, which is the super user command, apt get, so it's apt with a little dash and then get, and then update. So what that will do is it will go on to the package repository online, and it'll check to see has it got the latest package repository catalog file. Got a very noisy chair. I don't know if you can hear that when I do that. I always think, should I apologise for that sound? So yeah, just go and grab in the latest package list, catalog, inventory, manifest, whatever you call it. Usually a bit quicker than this, to be honest. And then the next thing we would normally do, I probably won't do it now because it will take a bit of time, is you do apt-get upgrade. So if it's found in these packages that there are newer versions of them, upgrade will upgrade them. I did this before, was it yesterday? Yeah, on Saturday I ran this, so there shouldn't be really that many new things there, but people are updating these things all the time. So if you just press the up key, we can just do upgrade. Well, like I said, I'm not actually going to say yes to this if it finds any, but normally it will say, do you want to do this? It's like 24 meg, blah, blah, blah. There you go, 25 meg worth of stuff. Do you want to upgrade these? So I'm going to say no at the moment, but normally I would say at this point, say yes to make sure you're on the latest version of everything. Right, let me just get my cheat sheet open on the side so that I can follow along. So if I just go to the action.smarsfan. Sorry, I've got that saved somewhere. Let me just go back to here for a second while I just pull that up. I've got the original, you see, I can just dip into that. Okay, so OpenCV sheet PDF. Wait for that to come on there. Should have had this prepared in advance, so I didn't keep you waiting for a second. I always hate it when there's a sort of bit of dead air and nothing's happening. And because I've moved into this new Mac, I haven't got all my shortcuts where I want them to be, so I'm having to just find stuff. So I am quite organised with my files though, so it shouldn't take me too long. So it's in web, it's in SMARS Fan Jekyll. I use Jekyll to generate my website for those people that are interested in that, and then it's in there, and there is the cheat sheet. Okay, right, so what I've done is let's just share that for a second. So I've installed the update. Just bring that across there. So what we need to do now is install all these libraries. So you can see there's quite a lot of libraries to install. Let's see if I can grab that, copy that and paste it. That'd be really nice if I could do that. Nah, of course I can't do that. Okay, so let's just type this in. So it's sudo apt-get install and then build essential and check install make package. These are all the names of libraries that we need to get, or packages that we need to get. Oops. Check config, and git is the first one. This slash just means we're going to go onto a new line, so it understands what that means. We need something called gfortran. Anybody know what Fortran is? We need libjpeg8 dev. We need libjasper dev. We need libpng 12 dev. We need libtiff. Does anybody know what these are as well? The PNG, TIFFs and JPEGs. And we need libtiff.dev. So there's 5 and without 5, and then there's lib av codec dev and lib av format dev. Let's just do that. And we also need lib software scale dev. Nearly done. Lib v4l dev. Not sure what that is. And lib atlas dev. Base dev. All your bases belong to us. And then vid core dev. And then ... Right, let's see if this is going to work. So what that's going to do, what's it not like in there? Unsupported file ... Okay, do with that then. So yeah, it's going to grab all of those and try and install them. If I've typed any wrong, it will tell me. So G4tan is Fortran, not Fortan. Let me just correct that typo. So Fortran, if you know what that is, that's a formula based programming language from the from the 60s, 70s. It's quite a popular one with academia. It's kind of a forerunner to things like Python. So you can see a lot of these are already installed, so that's good. It shouldn't really come up with any of these conflict things, that's fine, don't worry about that. So the next step after we've installed all those libraries is we need to change the swap size. So what the swap size is, in your Raspberry Pi you have about half a gig of RAM, and to compile this we need at least a gig of RAM to compile it, because there's quite a lot of code for it to sort of maintain in its memory. So it has a swap file, and the swap file is really small to begin with. It's because they use SD cards, and SD cards are not really designed to be written to hundreds of thousands of times. They have a life, so the more that you write to them, the less life they have. And a swap file is something that you use instead of memory, so you would write that out lots of times. So on a Windows PC, on a Mac, they have swap files. On a Linux PC, have swap files as well, and it's just a way of pretending that you've got more memory than you actually physically have. It's called virtual memory. So on a Raspberry Pi, we keep that quite small. I think it's normally about 100 meg. Sorry, 100. Yeah, it'd be 100 meg, won't it, instead of a gig? And we want it to make it a gig in size. So the way that we do that, let's go back to our screen share. To that one. There's not much I can. Let me see if I can zoom in on that. Actually, I might be able to zoom in on that to make it a little bit bigger. There we go. That's better, isn't it? Right. So let's just clear that screen. So what we're going to do, there's a command called sed, which is a way of editing files by sort of saying I want to replace one thing with another. So that's what we're going to use sed for. We are going to we need to type sudo in front of it actually, because it's going to change a system file. The swap file is a system file. We're going to do I for interactive, and we are going to say so conf swap file equals, where it currently equals 100, we want you to change that to conf swap file equals 1024, which is the rounded up version of a gig. So that /g, and then the file that we want to edit is called etc, and then dfizz swap file. If I press tab, why is that not auto correcting that? Ah, sorry, I've done that wrong. It's the wrong slash. Swap file. There we go. So it's going to just change that one line from 100 to a gig. And we're only going to do this temporary because we don't want to ruin our SD card. These things are not free. We now need to stop the swap file service and then restart it. So that's what the next command does. If I just show you that. Oops, where's that gone? I just press that. Yeah, you can see there we need to say sudo inside the etc initialization daemons folder. get the physical swap file and stop it, and then start it. So that's what we need to do next. So let's go back to, that's probably the best one, isn't it? Right, so let's do that. So sudo etc initd, initd dfizz, swap file, stop. And then it's going to stop that, and then we can just do start. So we've now got an extra gig of RAM in theory for us to play with. So now we need to actually get OpenCV. So I'm going to go into my documents folder, and I am going to clone a Git repository. So we've talked about Git in the past. Git is an open source source code control program, and GitHub is kind of a cloud repository of Git. A cloud storage of Git repositories, something like that. Go to github.com, you can sign yourself up for free there. You can follow me, you can follow other people as well. So let's go to git clone, and then we type in the address, which is github.com/opencv/opencv.git. And what that will do is it's going to clone the latest source code that they put up there down onto our Raspberry Pi. It doesn't take too long for it to do. It's not a massive file, but it's not instantaneous either. A quick sip of my drink while we do that. And just while it's doing that, I'll just show you on the overhead as well. What I've had to do on here is, oh, you can't quite see it, this camera, I've just put a bit of blue tack on the back of it so I can stick it to this pole so that it can actually see me. What I have done on this, our actual quad, I wasn't happy with the camera module mount that kind of comes with the what am I trying to say? That comes with the files. So the one that Kevin Thomas designed, it's not actually designed for. Sorry, it's white and you can't really see that very clearly. So yeah, the back of it, for example, snapped off on the one I printed out, and you can't fit a Raspberry Pi camera into this. So from my point of view, it's utterly useless. So what I've done is I've got a Raspberry Pi camera. Here's one I prepared earlier. So I'll just grab that. I get my trusty calipers. If you haven't got some calipers and you're into design, you really need some. So these are digital calipers. So if I just switch that on, you can see that it has like a little counter, and depending on what the size is, you can very accurately measure. So if I put this in here, I close this up, it's somewhere about 25, 26, is it? 23 even. So that's not quite 24 centimetres, 2.4 centimetres or 24 millimetres. It's not quite, and that's because it's not that precisely manufactured, but this can tell you very accurately what things are. And I don't know if you've used calipers before, you've got the main sort of mouth part there, the main part that can measure it, but you've also got these other ones for measuring things like, if you want to measure the hole there, you can stick that side in, and it will then tell you precisely how big that hole is. You've got another pointy bit on the end as well, and that's for sort of measuring depths of things. So if I want to know how deep the hole in here is, there's a little hole inside. What I can do is just open this out a bit, put that in there, and then close it until that comes to the sort of top part. And I can see there it's pretty much 12 millimeters. So I know that that's quite a precise piece that's been made there. So what I did is I measured the actual camera, modelled that in Fusion 360. If we've got time, I'll show you that model. I'll certainly share that on Thingiverse as well, so that you can get a copy of that. And I printed my own version that actually does fit Raspberry Pi camera. Excuse me. So if I put that in there, and I put my thing together, it will fit a Raspberry Pi camera. So there's actually a camera in there. Put it in the wrong way around, of course, like a moron. There we go. And I've also made a little hole at the back for the cable to go through. So if I actually put it the correct way round and then show you again, you can see that the lens is exactly in the right place, and on the very back there is an area for the ribbon to come out. So that's what I printed out and put onto my Raspberry Pi there as well. Right, so, oh good grief, is it still downloading? Right, this isn't a big, it's like 50 meg or something, is it? No, it must be more than that. It must be, if it's doing, well, we'll have a see. This was a lot quicker than this last time. So while that's down, and this is why I've created the cheat sheet, because quite a few of these steps take a long time to do. I wasn't sure how much of this we would actually get through. So let me just go to share the actual cheat sheet with you again. So you can see there we need to clone 2 files. We need to get the GitHub, the OpenCV source itself, and then there is like an extra modules bit that we can download too, which if I can just move this about a bit. There we go. Sorry, let's just zoom in on that. Trying to make it so we can see it. There we go. OpenCV contrib, that's like the contribution, and in there's some extra modules to enhance OpenCV. Once we've downloaded those, that really shouldn't take that long to do. Once we've downloaded those 2 things, we then need to create a build folder. So if you've done any Linux or Unix before, creating folders should be quite trivial. You just use the mkdir command, make directory, and we want to make a directory that's called build, and then we want to change directory into that CD. And once we've done that, this is where it gets interesting. So we need to create a make file. So we use this cmake /d, and then we type in all these commands here. And what that tells the make command to do is to look at all these source files that we've just downloaded, and from that we want it to configure the OpenCV for our particular machine, because this open source software can work on any machine. It can work on Windows, it can work on Macs, it can work on great big mainframes or tiny mobile phones. It can work on all kinds of things. So what we're actually telling it here is precisely what parts of the modules that we want to use. So we're saying install it in this user local folder. We're saying make sure the Python examples are on, make sure the C examples are off, and then use the extra modules folder, which is in that OpenCV contrib /modules folder. And build examples also we want to switch on. And it'll take it maybe 5 minutes to generate that make file. Once it's completed that, we go to the next page. We then get to the bit that takes the time, which is the making itself. So when you do make /j, the $nproc thing is if you've got a Raspberry Pi that's got more than one processor, because it's basically just saying use whatever the variable is for the number of processors. So if you do /j4, which is what you can do on a Raspberry Pi 4 because it has 4 cores, it will use all 4 cores to compile. A Raspberry Pi Zero just has 1 core, so you can just do make /j and that'll work fine. But it takes a long time to do that, so fair warning, I would set this going and have it so that it's undisturbed. You don't want to be pulling any wires out or anything like that and messing with it in any way. Just let it get on with it. And you also need to make sure, because it's going to be using quite a lot of the Raspberry Pi capability, you need to make sure it's got a proper power supply. So if you're just running this from like a mobile phone charger, make sure it's got at least 2 amps worth of power to supply the Raspberry Pi Zero, and that should be sufficient for it to do its compilation. Once we've done that, we then do the make install, which takes that compile thing and then actually installs that onto our machine in that location that we've asked it to. So once we've done that, we then need to revert our swap file back to the 100 meg that it was instead of the 1 gig. So that sed command there. And again, you can get this PDF so that I don't have to sort of explain all these things. You can just by going to action.smarsfan.com/OpenCV. Get your copy there. And once we've done that, we then create a virtual environment. So again, this is something that might seem a bit complicated to do. When we have a machine like a Windows, a Mac, a Linux or a Raspberry Pi, it might have Python installed on it, but we don't know what version of Python that is. So we want to very carefully control that Python environment. So we do that by creating a virtual environment, because we can put as many different libraries in there that we like, and it doesn't interfere with the system level libraries. So what we essentially do is create a folder, and this one I've called it test, I think. I've gone into the test folder by doing cd test, and then I've said Python. It should actually be Python 3. I think I've got a corrected version of this that's on the website. Python-m, which is kind of create me a virtual environment that's called venv. So venv means create me a virtual environment that's called venv. Once it's done that, we can activate it by saying source venv/bin/activate, and that will create the that will make sure you're actually using the virtual environment. And then we can do things like pip install numpy. So pip is the package manager for Python. I know there's a lot of information coming at you here, so stick with me. This is why there's a cheat sheet. So pip is the package manager for Python, and numpy is one of its sort of mathematical libraries. It's a very large sort of scientific library that can help with all the kinds of things that we're going to be doing, like the sigmoid function, for example. So numpy is something that we really want to have installed in our Python virtual environment, and pip install numpy will do that for us. And once we've done that, we can then type Python import cv2 print cv2 __version _ brackets, and it will tell us that it is installed. So that's all the steps that we need to do. It does take quite a while to do those steps, I appreciate it. And, you know, I've only got an hour in which to communicate a lot of this with you. And the results are that we can then go to our Raspberry Pi. So if I go back to our Raspberry Pi Black, we can then do things like, in fact, that little blue tap thing has just fallen off. So let me just stick that back on there so we can take another picture. So, it's like selfie time, this. So if I want to show you that this is a live demonstration and it's not something I'm actually making up. So if I don't know, if I take a collection of objects or something, just so you can see next to my face that this is actually happening live. So I'm going to go back to the screen share, and then I'm going to press the, let's just show you what I'm going to do. So I'm going to just press return on there like that. And then let's see, so it's found a face. Let's go to open that up. And let's see if it's got that collection of stuff. Good grief, that's a really unflattering picture, that. Let me take that one again. So let's just run it again. Let me just suck my stomach in this time. Okay, let's see if it's done that this time. That's better. It's, even though my face is blurred, it's still found it. And think about the steps that it's going through there as well. It's taking that image. And this is quite a low resolution picture to begin with. We purposely said only get an image of 320 by 240 pixels. We're taking a really, really low resolution picture. Raspberry Pi cameras can take really high resolution photographs. This isn't really high resolution, but we've done that on purpose because we don't need all that high resolution to do face detection. Actually, it gets in the way. It's much easier just to have less information to start with. We then convert to the grayscale. We then take that array of pixels and we start putting that into our model. So OpenCV comes with a face detection already pre-trained model. So if you think about that slide that we had open a minute ago, let me just go back to that one so I can show you exactly what I mean. Make sure I've got. I zoomed in a bit there. Let me just zoom back out. Oops. Sorry. There we go. Zoom back out. There we go. So if we jump back to which bit am I looking at here now? This model. So this model here, we've got our data coming in from the left-hand side, and then we're training it by adjusting these weights. So the model is this entire thing. It's all the weights added to, all the weights and all the number of neurons that we have defines what this model is. And all we then need to do is put a single image in one side, and it can then say, based on the weightings that we've got, the output is there's a face in this image and it's at these coordinates. So it gives you kind of a rectangle of what the coordinates are. If it detects many, it'll give you an array of rectangles. So that entire model we can save. Now, when we want to create many models, we have to provide that training data. So one of the things I created, and this is how I got into sort of machine learning, only about a year ago. It was about this time last year, actually. And I was working with a software company. Shout out to Loculus, an amazing software company who make call center software, amongst many other things. And one of the guys there, Tim, he said, we had a bird table outside the office that people like to sort of put food on, and we'd sort of see the local bird life and stuff, go and, eat food there. And he said, wouldn't it be really cool if you had like a Raspberry Pi with a camera pointing at this bird table, and it could count the number of birds that come and eat there and sort of log the time. And it'd be even better for like bonus points if it could say what kind of species it was. And I was thinking, you can do this. You can do this with OpenCV or maybe something like Google TensorFlow. And I thought it's just a matter of figuring it out. So one of the myths about machine learning and artificial intelligence is that you have to be some kind of really smart data science to use it. You really don't. It's just like a black box. It's just Lego bricks that you just plop together. And the bit that's hard is just wiring these things together. You don't have to understand anything about how these things work other than these are the steps you need to go through, which is why I've got you the cheat sheet. Just follow those steps and we'll get you up and running with OpenCV on your quad, or any Raspberry Pi actually. You don't have to have it in a robot even, you could just have it with the camera. But it's more fun, I think, in a robot. So what I did with this this particular project was, and I call it TwitcherPi. You can go on my GitHub repository and download the files if you really want. And I use TensorFlow, and TensorFlow is just the sort of apparatus. It's all those neurons. It's all the training algorithm, all that kind of stuff. There's lots of options for that, because that training algorithm, depending on what you're trying to do, so I'm doing object detection and classification. So those two things require a specific type of trainer. So there's lots of different ones you can pick, and if you go onto the sort of forums and you learn about this, they'll say use this one. This is the best type of trainer. Excuse me a second. So I downloaded TensorFlow on my Mac Pro, and it's just here next to me. This is my old Mac Pro that's now no longer being used because I've got a nice shiny new one. So yes, I downloaded TensorFlow, and I was like all set up, ready to go, and I wanted to build my own AI, my own neural network. So for this particular thing with bird tables, so I needed some training data. So I spent an entire weekend downloading 1,000 pictures. I had to get, I decided that I wanted to have 10 types of, what is the top 10 common birds for that particular region. So in the UK, it might be like blackbirds, starlings, blue tits, great tits, whatever else there are. I knew these because I spent so long bloody drawing rectangles around them. Sorry for my language there. It was a lot of effort to do this. Anyway, so what I had to do was get these 1,000 images, put them into folders to say that this is a starling, and there's 100 pictures of a starling, and then with another piece of software, I would have to get that image up and then draw a rectangle around where the image, the actual image of the bird is. So where is the object within this particular picture? And that creates a little XML file that just says these coordinates, there's a blackbird. So there's like a tag. So I did that for all 1,000 pictures, for all those 10 different types of species, 100 pictures for each of them. And then there was another step where you had to then sort of crunch all of those XML files into a single file, and then that was ready then to train the model. So it would then take half of the images and it would train the model, and it took it about 3 days of intensive, my CPU was like 100%, all 8 cores, for 3 days, red hot, as it was crunching through all these different training scenarios. And at the end, it had a model that would perfectly find birds and classify them within these 10 different species. Now, the thing I learned from this, I'm nearly at the end of my my little story here. The thing I learned from this is that people only take pictures on and put them on the internet of birds. They're either face on or side on. They never take pictures of the backs of the birds, because who cares about the back of a bird? However, when birds are eating at a bird table, they're most likely going to be having their face away from you, or their back towards you, or the side towards you, in kind of unflattering, blurred angles. So that's the reality of that particular scenario. I would have to take my own pictures from a bird table to be able to then classify them for that to work a lot more accurately. So it was very good at accurately detecting pictures of birds that were professionally taken with the bird either head on or some kind of side angle. That's it. But I learned exactly how you make neural networks using TensorFlow. And it was just a matter of putting these bricks together, as it were. So, what else was I going to say about that? Let's just have a quick look on, see how that was up to with its downloading of the Git repository. So it's done that first one. We then need to do the next one. I'm not going to complete the whole thing because we'll be here all night if I do this. But essentially, we need to follow those steps that are in the cheat sheet. So again, action.smarsfan.com/OpenCV. Get your copy of that, and you can be up and running with that. And then, yeah, you can be detecting faces and doing stuff with that. So my next step is to integrate that software into our SMARS lab, so that we've got an extra little tile that you can see what the picture that's been taken, and we'll get it to take pictures as often as it can, or have a live video feed and draw the rectangles. We are kind of at the mercy of, just how accurate, how fast the Raspberry Pi Zero is. Can it do real-time object detection? Not sure. So yeah, where I was going with that story before, I just remembered, I've lost my thread a bit there, was that with OpenCV, they have a face detection model that they provide you with. It's called something like HAAR, Full Frontal Cascade, or something like that, .xml. And it's about 24 meg in size, and that is the model that they've already trained very, very well to detect faces. So have a play with that. It's great fun. I'll continue to upgrade SMARS Lab so that it can integrate that, and we'll have our little robot being able to do things like detect a face and maybe move left or right, or move towards the face if it sees a face, something like that, so maybe it can follow us about if we're looking at it. And next week we'll be looking at how to do speech synthesis and speech voice recognition using similar kind of libraries to this in Python. And we'll need some way of getting sound in and out of our Raspberry Pi. So one of the things I was showing you just at this sort of pre-show countdown was a number of years ago, on the front of the Raspberry Pi magazine, MagPi, was this little kit by Google, and it's essentially like a Google Home device, but you have to press to talk. So they didn't want to sort of outdo themselves and give this stuff away for free. So in here there's a little hat, as they're called, which is a bit like a shield for an Arduino. This is a hat for a Raspberry Pi. So there's the header pins there. We can see this. It's called Voice Hat. And it's sort of a purpose-built thing. There's a great big speaker inside as well there. There's the push button, which is really just, I don't know if you can see that. It's just a micro switch. And it has... it illuminates, it's lit up as well, so when it sort of glows, you can do all that kind of clever stuff with it. And in here as well, there's a little array, 2 array microphones. So there's microphone left and microphone right, so that it's got a bit more to it. And the idea is you put your expensive Raspberry Pi in there, not the Zero, the sort of full 2 or 3. It probably needs a 3 to be fair, this one. It's quite processor intensive. Made a dog's dinner of that. And yeah, the idea there is you can then create your own, Google Home device, and you press it and you can talk to it and ask it questions, and it just connects to Google's cloud voice services and brings back anything you ask it. So it's quite a nice little project to do that one, and it's made of cardboard. It's very simple to put together. They had that on the front of the magazine. So that has a dedicated hat for getting sound in and out. So for our Raspberry Pi Zero, you can get something like this, which is called a speaker fat. And This one is by, is it Pymaroni? So I don't know if you can see on the back there. It's by Digital to Analog Converter Speaker and Amp by Pymaroni.com. So on the back there, that's the speaker, and then on the front, you can see my really bad soldering on there actually. On the front there, there's like a little LED gauge that as the sound is sort of coming out. It's mono, it doesn't have two. It kind of looks like it's got two speakers. It's just a singular speaker. It doesn't have a microphone on it though. It is just for sound output. But we need something like this to be able to get sound out of and sound into our Raspberry Pi. So I'll be looking at that next week and recommended options that you have. I do understand that a standard Raspberry Pi, there are a couple of pins on it for doing things like video and audio in and out. I've got a feeling there's like 4 pins just there, which are the TV pins, I think it calls them. I'm pretty sure they're sort of composite audio, composite video and composite audio. So we might just be able to take some header pins and put them on that, get that working. I shall look at that for next week, one bit at a time. And while we're looking at these hats, so that's the speaker fat. You can get loads of these sort of add-on hats. So this is one I ran, good grief, 2 years ago. Was when it was last connected, and this one is a Inky Fat. And what the Inky Fat does is it's like your Kindle, so it's a digital ink screen, but it can keep the image without any power. So it just changes what the image is. It doesn't need any power for that image to stay. It kind of fades over time, but that is from 2 years ago, and that's a white, black and red image, and you can see that I ran that on the 29th of December 2018, which is 2 years ago. Another one I purchased a while ago was a LoRa node. So LoRa is for sort of long range radio, and you can get this a better angle on this. And what this means is, and there's actually a Raspberry Pi, sat on that as like a sandwich. So what this means is you can transmit data, like a kilometre, something like that, maybe 10 kilometres, just using this tiny little antenna, free. You don't have to pay any kind of cellular. It's just using normal, the same band as garage door openers and things like that. I think it's like 433 megahertz, something like that. And there's a few different bands that it can use, but it's, in fact, it says on there, this one is 868 megahertz, so whatever standard that is. And they've made these so that in, I think, almost all countries around the world, you can use these without any kind of license. So it's quite cool. Not talking massive data transfer, but for something like a weather station or something, you can transfer enough power, enough data across on that. And the low power, that's another part of them as well. I've got one of these sensor hats. This is really fun. So this one is for the sort of larger Raspberry Pi. So this is a, what does it say on there? Sensor Hat version 1. So you've got this nice 8x8 matrix display, not unlike our SMARS Robot 8x8 display for its face. You've got a little joystick on there as well for controlling up, down, left, right. I think it has temperature, humidity. These actually work as a light sensor as well. LEDs can always be light sensors. And I think it also has like digital compass on it as well. So there's like all kinds of clever stuff that you can do with that. Loads of fun. And not to be outdone, is this Pymaroni again? Yes, this is another Pymaroni thing. So they've created this thing that they call the breakout board. And this sits onto your Raspberry Pi like a normal hat. And then you connect these extra modules to it. So you can see there's an OLED display, and then another one next to it is an accelerometer, gyroscope and compass. And these all use the I2C bus, and you simply just push them in like so into the little header. You can see there, so we've got a 1.2 inch OLED display, and we've got a little sensor next to it as well, and there's a space for an extra thing. So these are tons of fun. They obviously sell these little things that slot into it. it's good for sort of experimenting with stuff. So just thought I'd share that with you. I thought that'd be an interesting thing to sort of cover off. Cool. So let me just go back to my slides and see if there's anything else we need to cover off, because I think there was. So if I go back to my slide share. So we went through all that. So of course, like, comment and subscribe. So if you're getting good value out of these videos, if you enjoy what I'm doing, please make sure you subscribe to the channel as a minimum. Be nice if you like the video as well. The more likes I get, the more I get out of that, and I understand. And if you do the little bell thing, you get a notification to say that either that I've put a video live or that I'm going live. So you get notification of that. And I've now started putting other videos up as well, all to do with robotics. I did one about an unboxing of my new Mac Pro. That was good fun, MacBook Pro. And I also did one about the InMove robot that I'm currently building. So, you know, you'll get all those things as well. So please, please, please subscribe. It really helps the channel growth. It makes the algorithm pick up and share with more wider audience, the more people that like, comment and subscribe. So yeah, I really appreciate it if you do that. And the other thing that's really cool is Svineborn was saying, wow, what a workspace, Kevin. Haven't seen your latest stuff, been busy with new school, doing a computer science degree. So awesome. Computer science is one of the best degrees you can do. I did one probably about 20 years ago now. That seems like a ridiculously long time ago. But it was one of the best times of my life because I got to sort of just be thoroughly embedded and learning all about, you know, computer science. I absolutely loved it. So good for you for doing that. I hope that studying's going well, but you know, you can always find a bit of time to come and watch the videos. So let's have a look what we have for you next week. So yeah, if you're building along, this is all about build with me. So make sure you're up to date with the current video. Get yourself the OpenCV cheat sheet. That can really help you do what you need to do to get OpenCV up and running on your Raspberry Pi Zero. I was hoping to be able to show you it directly from the quad, and I ran out of time myself. I was just fiddling about with something and I realised it was going to take 9 hours to build, and I was like halfway through Sunday, so apologies for that. I only have so much time myself at the moment to commit to this, so I'll get like basically a couple of hours a week and then the weekends to put the shows together. So that's why I'm saying please subscribe. This is all free for you guys. So yeah, and then the next step is getting some Raspberry Pi audio. So you get yourself a camera, one of the Raspberry Pi cameras or clones, so it can see, and get something which will help with the audio. So that audio hat that I've got there, I don't think it's going to work for one obvious reason, and that it sits on the Raspberry Pi, but it doesn't sort of share the pinouts beyond that. So how do we plug in all the stuff that we need to make the arms work and the camera work? That's going to be, but the camera's on a separate thing actually, but it'll just be the data and clock pins for the PCA 9865 board. So yeah, as long as we can get them plugged in, that will be fine. And that one was just for audio out. We need audio in, so I'll look into that as well. And I'll probably put a post up and share that with you. I'll probably update the video as well, notes as well down below. So there is a link at the bottom of the in the video description to this video for the cheat sheet. So if you click that link, you can get yourself a copy of that as well. Cool. So I think that's everything I have covered off for this week. What do you think about the new little me in a bubble? I'm slightly off centre there. Look at that. That's not right, is it? You can see I did this in a bit of a hurry just before I went live. So yeah, I've got the this is my normal host camera, as it's called. We can have it with a bit of background music. What does that sound like? That's not too bad, is it? I've not figured out how to make it have music on all the time while I'm changing scenes. As soon as you change a scene, it sort of kills it dead. And I always forget to turn the music off on the comment of the week as well. So sorry if that was blasting out and you couldn't hear anything. We have the overhead camera, and I'm now in a little bubble to sort of help with that, so you can see what I'm doing. And we can be looking at the things like, there's a little camera module that we've got on our Raspberry Pi, and there's the other Quad next to it. There's the Raspberry Pi Black at the back, which is the Raspberry Pi 4. These are all the hats we were just looking at. And there's my calipers, which I can't live without for doing design stuff. They helped me get that little camera module designed this week. So yes, and I've got this sort of new theme going on as well. So things like the overlays, they've got this nice little cloud and orange look and feel. It's like a sort of a fresh look to them. So interesting to know what your feedback is on that. So Sammy was saying, thanks, amazing as always. Keep it up, buddy. Thank you, Sammy. I always appreciate your support as well. I know you're always there sort of watching along as well, so I really, really appreciate that. I can't tell you enough what it means to have somebody with me when we do these live streams. And I know that not everybody can make the live stream, so if you're watching this on playback, please leave a comment down below. Let me know that you've watched it. If there's anything that you think about that you want to, was it too fast? Was it too slow? Do you want more depth? Do you want more videos with more content in them at a slower pace, or is this okay? I always like to know what you guys think about that. So let me just go back to my show notes a second and make sure I've not missed anything off. So we talked about the Pi hats, the camera design. I might do a separate video on the Fusion 360 design of that camera, because I know quite a lot of people have liked the design videos I've done to date. One guy, Chris, was really frustrated that he couldn't see what I was doing, so I will put more design videos up there because they've been quite popular. They were the first ones I did, so I'm a bit... are they popular just because they're the first videos I did, or are they popular just because people like them? So, and yes, so the other thing I need to sort of just make people remember is I go live every Sunday, 7 p.m. Universal Time or Greenwich Mean Time on YouTube. So I do post to a number of Facebook groups that I'm going live. But if you get yourself subscribed and tick the little reminder thing, you'll never miss a show. And maybe you want to binge watch these at a particular weekend or something, I don't know. So yeah, that's I think pretty much everything we need to cover off this week. So next week it's all about the speech synthesis and speech recognition without connecting to the internet. It's all on the chip. It's all on the Raspberry Pi. That's what makes this a bit different than the Google thing, which kind of cheats and uses, you know, massive cloud infrastructure. No, we're not doing any of that. Our little robot doesn't need any connection to the internet, and that's what makes this particular thing quite cool. So hopefully you've really enjoyed that. We're pretty much out of time this week. So thanks for watching. Thanks to James and Samo. Who else was on there? I think it was mostly just James and Samo. Thanks for watching along this week, and I shall see you all next week. So see you guys later.